How do factories mass-produce Reese's peanut butter cups, Ferrero Rocher, and Smarties without losing their signature bite? One tiny miscalculation in filling temperature or cooling speed can wreck the taste instantly. In this video, we follow each line from mixing and molding to high-speed wrapping, revealing the critical checkpoints that keep every chocolate perfectly consistent. The Reese's peanut butter cups process starts with peanut handling because peanut chemistry drives filling texture and oil stability. Roasted peanuts are cleaned with screens and air separation to remove shells and fines. The roast endpoint is controlled to set aroma and to reduce moisture so the paste is stable. After roasting, the peanuts are cooled quickly so residual heat does not thin the paste and does not accelerate oil separation. Grinding converts roasted peanuts into peanut butter. Nuts pass through staged grinders that reduce particle size while releasing oil to create a continuous fat phase. Temperature rises due to friction, so jackets and controlled throughput keep the paste within a narrow range. The paste is refined until it is smooth enough for the target mouthfeel. If particle size is too coarse, the filling feels gritty. If too fine, the filling can become overly dense and lose the characteristic crumbly bite. Filling formulation then turns peanut paste into a depositable mass that sets cleanly. Powdered sugar is sieved to remove clumps and to ensure a consistent fine size. Milk powders, cocoa powders, and salt are staged as dry micro-ingredients. A fat stream such as cocoa butter or another compatible fat can be used to tune firmness and melt. Emulsifiers can be added to stabilize oil distribution and improve flow through depositors. Mixing begins by combining peanut paste with dry ingredients in a high-torque mixer. Dry powders are added gradually so they wet without forming islands. The mixture transitions from glossy paste to a thicker, crumbly mass as sugar and powders absorb free oil. Mixing energy is tuned because it determines final texture. Overmixing can create a smooth paste that loses the signature short bite. Undermixing leaves dry pockets that cause weak structure and dosing errors. The filling is then conditioned for deposit. Conditioning equalizes temperature and allows fat crystals to form in a controlled way. If the filling is too warm, it flows and smears under the chocolate cap. If too cool, it becomes stiff and will not level in the cup. The line targets a narrow temperature band that supports clean deposits with sharp edges. The filling can be held in jacketed hoppers with gentle agitation, so it stays uniform without being whipped full of air. Chocolate preparation runs as a separate stream because shell quality depends on temper. Chocolate is melted in jacketed tanks and filtered to remove unmelted particles. It is then tempered through a staged heat and cool cycle that builds stable cocoa butter seed crystals. Working. Temperature is held tightly because viscosity determines shell thickness and because temper drift causes bloom and weak snap. Paper liners are fed to the forming line as a continuous stream. A denister separates liners and places them into cavities on a moving mold plate. The mold plate supports the liner so it holds shape during chocolate dosing. Liner position is controlled because misalignment causes thin spots and uneven rims. Forming the chocolate cup begins with depositing tempered chocolate into each lined cavity. Deposit volume is controlled because it sets shell thickness and final weight. After deposit, the molds are vibrated or spun to drive chocolate up the liner walls and create a thin, even shell. Spinning forces chocolate outward and leaves a hollow center. Vibration removes trapped air and smooths the surface. Spin speed and time control wall thickness. Too much spin makes walls too thin and fragile. Too little spin leaves heavy shells and reduces filling capacity. After shell formation, the cups enter a short cooling stage. Cooling sets the chocolate enough that the shell holds shape for filling. Cooling is staged so the shell contracts slightly without cracking. The shell must remain receptive at the interior surface so the filling bonds. If the shell is too cold, it becomes slick and can cause delamination at bite. If too warm, it deforms during filling and can smear. Filling deposition follows. The filling is dosed into each shell as a measured puck or mound. Deposit weight is tightly controlled because it defines bite and also determines whether the cap will seal cleanly. The filling can be deposited as a single shot or as a spiral. A spiral can improve leveling and reduce trapped air. The filling surface is controlled so it sits below the rim and leaves space for the chocolate top. A light leveling step can be used to control filling height. Leveling can be done by vibration or by a smoothing tool. The objective is a consistent fill height across all cups so the top chocolate spreads evenly. Leveling must be gentle because aggressive vibration can smear filling onto the rim, which contaminates the cap seal. Top chocolate application seals the cup. Tempered chocolate is deposited over the filling. The deposit must spread to meet the shell rim and create a continuous seal. Deposit volume determines top thickness. Too thin a top can crack and expose filling. Too thick a top can dominate bite and slow cooling. Some lines use a slight vibration after topping to level the surface and release bubbles. This vibration is controlled so it does not cause chocolate to climb over the liner edge. The filled and capped cups then enter the main cooling tunnel. Cooling is staged to promote stable cocoa butter crystallization and prevent bloom. Early cooling sets the surface quickly so the top does not slump. Later, cooling removes heat gradually so the entire chocolate mass crystallizes uniformly. If cooling is too fast, internal stress can create fine cracks around the rim. If too slow, throughput drops and cups can scuff in handling. During cooling, the peanut filling also stabilizes. Fat in the filling crystallizes and locks the short, crumbly texture. Moisture migration is minimal because both phases are fat continuous. The main interface risk is oil migration that can soften chocolate if the barrier is weak. Stable temper and proper cooling reduce this risk by creating a tight crystal network in the chocolate. After cooling, the cups are demolded. The mold plate releases the lined cups and they transfer to conveyors. Handling is gentle because the rim can chip. Vision inspection can check top coverage and detect deformed liners. Weight checks confirm dosing stability. Metal detection can be placed before wrapping. Wrapping depends on format. Individually wrapped cups are fed into a flow wrapper that forms film around each cup and seals it. Seal temperature and dwell are tuned so the film closes without melting the chocolate surface. Film tension is controlled so it does not crush the cup. For multi-packs, cups are collated into groups and then overwrapped or cartoned. Trays can be used to prevent movement and rim damage. After primary packaging, packs are coded and checked. Check weighers confirm net weight. Vision systems verify seals and codes. Finished units are case packed and palletized. Storage temperature stability is important because warm conditions soften the filling and stress the chocolate temper. Stable storage preserves snap and prevents bloom. The critical controls in Reese's cup production are peanut paste consistency, filling temperature and texture, chocolate temper, shell thickness, and cooling profile. Peanut paste consistency and dry ingredient ratio determine filling firmness and short bite. Filling temperature determines whether deposits are clean and whether oil separates. Chocolate temper determines gloss and snap and bloom resistance. Shell thickness determines structural strength and the chocolate to filling ratio. Cooling profile determines crystal stability and demolding reliability. Ferrero Rocher is built by synchronizing 4 separate manufacturing tracks that converge only at the assembly belt: roasted hazelnuts, wafer shells, hazelnut cocoa cream, and tempered chocolate for coating and adhesion. Hazelnut preparation starts by turning raw kernels into 2 distinct inputs. One stream becomes whole center nuts, and the other becomes chopped outer pieces and paste for the filling. Incoming hazelnuts are cleaned with screens and air separation, so stones, dust, and shell fragments are removed before roasting. The nuts are then graded by diameter. Tight grading matters because the center nut must fit the wafer cavity without stressing the shell or shifting the final mass balance. Roasting develops aroma and sets crunch by driving down moisture. Nuts travel through a roaster with a controlled temperature curve, so heating is even from surface to core. Roast endpoint is chosen to create a crisp bite without scorching oils. Immediately after roasting, the nuts are cooled in high airflow beds, so residual heat does not continue cooking, and so the nuts do not warm the cream during later insertion. Skin removal follows because loose skins create bitter flecks and interfere with adhesion in the outer nut coat. Nuts pass through rubbing rollers that loosen skins, then aspiration pulls skins away from the heavier kernels. Whole nuts are separated from broken pieces. Whole nuts go to the center insertion system, and broken pieces go to chopping and paste lines. Chopped hazelnuts for the exterior require a narrow particle size band. Roasted kernels are cut with calibrated knives or granulators and then screened. Oversized pieces are returned for further reduction, and fines are removed because fines behave like dust and reduce visual definition. The chopped nut bed is held dry and free-flowing so it can coat evenly when the chocolate is still tacky. In parallel, a portion of roasted nuts is milled into paste. Milling is staged so particle size drops gradually, while temperature is controlled to prevent oil separation. The paste is refined until it is smooth enough for a cream with no gritty perception. Wafer manufacturing runs independently because wafer is a dry, brittle structure that must stay crisp through later contact with fats. Wafer batter is mixed from flour, sugar, water, and small fat additions to reach a thin, pourable viscosity. Mixing aims for uniform hydration rather than gluten development because gluten would make wafers leathery. The batter is filtered to remove lumps that would create thin holes in the baked sheet. Baking takes place on heated wafer plates that cook the batter into very thin, porous sheets by rapid water evaporation. The bake profile targets low final moisture, so the sheet becomes rigid and crisp without scorching. Forming converts wafer into shells with consistent thickness and rims. One approach presses warm wafer sheets into hemispherical cavities, while the wafer still has slight pliability. The pressed halves are trimmed to clean rims because rim quality determines seam strength. Another approach uses shaped baking plates that form shells directly, then trims edges to uniform height. Either way, cracked halves are removed because small cracks become leak paths for cream and also become weak points during coating. The good halves move to a joining station where two halves are aligned. Shell joining creates a hollow sphere that must survive filling and coating. A thin ring of adhesive is applied to the rim. The adhesive is typically a fat-based compound or chocolate-based film that bonds quickly without wetting the wafer. The two halves are pressed together with controlled force so the seam closes without crushing the wafer wall. The joined spheres pass through a short cooling zone so the seam sets and the shells become rigid enough for filling. The hazelnut cocoa cream is produced as a fat continuous paste that must be smooth, stable, and pumpable. Hazelnut paste is blended with sugar, milk solids, and cocoa components. Refining reduces the particle size of sugar and solids so the cream feels smooth rather than sandy. The mass is mixed under controlled heat to distribute fats and to reduce moisture that would thicken the cream unpredictably. The final viscosity is tuned so it can be dosed precisely into wafers without trapping air pockets. The cream is held in jacketed tanks with gentle agitation so it remains homogeneous and does not develop surface skin. Chocolate for coating is prepared and tempered as its own process because stable crystals control set speed and surface quality. Chocolate is melted, filtered, and then tempered in stages to create stable seed crystals. Working temperature is set so viscosity remains steady at the curtain and so the chocolate stays tacky long enough to accept chopped nuts before setting. Assembly begins at the filling belt, where wafer spheres are indexed and presented to deposit heads. The first cream dose is applied to create an inner bed. This dose must coat enough of the interior to support the nut and to reduce rattle. The nut insertion system singulates whole nuts so they feed one at a time. Each nut is centered and placed into the cream bed with controlled depth. Depth is important because it determines how much cream surrounds the nut and whether the sphere remains balanced for enrobing. A second cream dose fills the remaining cavity around the nut. The deposit pattern is chosen to avoid trapping air, often by laying cream along the inner wall and then finishing the center volume. Air pockets can collapse later and create dents that show through the coating. Once filled, the opening is sealed. Depending on line design, sealing can use a wafer plug bonded with cream or a chocolate plug deposited to form a barrier. The seal must be flush so the sphere rolls smoothly and does not snag when entering the chocolate curtain. The filled spheres are conditioned and cooled before coating. This step firms the cream and stabilizes the wafer seam so the sphere does not deform under the weight of chocolate. Cooling is staged to avoid condensation because wafer absorbs moisture quickly. The aim is a firm center with a dry exterior surface, so coating adhesion is predictable. Chocolate coating is applied by enrobing. Spheres pass through a chocolate curtain that coats the surface. A wire belt supports the pieces, while excess drains away. Vibration under the belt can smooth the coat and help bubbles escape. Air knives can trim excess and control the final thickness. Thickness matters because it determines the bite balance and provides the adhesive layer for chopped nuts. Nut application happens immediately after enrobing while the chocolate surface is still tacky. The spheres roll through a bed of chopped hazelnuts or receive a nut shower from above while rotating on a moving bed. The goal is full coverage without clumps. Feed rate and bed depth are tuned so nuts embed into the chocolate rather than merely resting on top. Too rapid setting causes poor embedment and later shedding. Too slow setting allows nuts to slide and create bare patches. Cooling tunnels lock the structure. The first zone sets the chocolate surface quickly so the nuts stop moving and coverage becomes fixed. Subsequent zones cool more gradually so cocoa butter crystals form in the stable state and contraction stress stays low. Proper cooling prevents cracks around nut peaks and keeps the surface gloss stable. During this time, the internal cream continues to firm as its fat phase crystallizes. The wafer remains protected because the cream and chocolate act as moisture barriers once set. After cooling, loose nut fragments are removed by gentle air brushing or screening so wrappers remain clean. Inspection checks look for incomplete coverage, deformed spheres, and weight anomalies that indicate missing nuts or underfill. Defective pieces are removed before wrapping because once wrapped, they cannot be visually corrected. Each sphere is then seated into a paper cup. The cup is a mechanical protection layer that reduces abrasion and keeps nut pieces from rubbing off during high-speed handling. The cupped spheres enter foil wrapping. Foil is formed around the piece and crimped into a tight seal. Tension and fold geometry are tuned so foil conforms around the textured surface without tearing and without compressing the sphere. Wrapped pieces are collated into trays where each pocket prevents movement. Trays are inserted into cartons, and cartons are closed and case packed. Smarties are engineered from the outside in because the crunchy shell is built first as a process target, and the chocolate center is engineered to survive the shell growth cycle without deformation. The manufacturing line begins by defining the core size and density that the shell system can coat predictably. Chocolate ingredients are assembled into a fat continuous suspension where sugar and milk solids are dispersed in cocoa butter. The mass is refined until particle size is below the gritty threshold. Conching then stabilizes flow by fully wetting particles with fat and driving off residual moisture that would thicken the chocolate later. Tempering follows, so cocoa butter crystallizes into a stable form. Stable crystals matter because the center must stay firm while tumbling for long periods during shell building. Centers are formed as small lens-shaped pellets with tight mass control. Tempered chocolate is metered through deposit heads into shallow cavities or onto a cooled belt. In cavity forming, molds are vibrated so air bubbles rise and the surface levels, then the pieces are cooled until they release cleanly. In belt forming, deposited portions are shaped by calibrated rollers that control diameter and thickness. Regardless of our method, the key outcome is uniform geometry. Uniform geometry means each piece rolls the same way in the panning drum, which is what keeps shell thickness uniform. Fresh centers are conditioned before coating. Conditioning holds them at a temperature where they are hard enough to resist dense, yet not so cold that rims chip. This temperature window also prevents surface condensation. Any surface moisture would disrupt the first shell layers and create rough adhesion points. Conditioning tunnels use controlled air, so the center surface is dry and stable. Shell growth begins in rotating pans or perforated drums, where centers form a rolling bed. Drum speed and fill depth are tuned so pieces cascade and roll rather than slide. Rolling exposes every surface evenly to spray and drying air. Sliding produces flats and uneven build. The mechanical motion is therefore treated as a process variable equal in importance to syrup composition. The first shell layers are designed as an adhesion bridge between chocolate and sugar. A very light sugar syrup is atomized and applied in short pulses. Droplet size is kept fine so the film spreads thinly and does not pool. Immediately after spraying, dry air flows through the bed to evaporate water and initiate crystallization. These early layers must set fast enough to prevent pieces sticking together. They must also avoid adding enough water to soften the chocolate surface. Once adhesion is established, bulk build begins. A higher solid syrup is sprayed in measured increments. After each spray, fine sugar is often dusted onto the wet surfaces to absorb moisture and increase build rate. Airflow then removes water and drives crystallization through the new layer. The cycle repeats many times. Each cycle adds only a small amount of thickness, so stress stays low and cracks are avoided. Crystallization control is central to shell quality. If drying is too aggressive, the surface can crust while moisture remains inside the layer. Trapped moisture later causes pits and weak zones. If drying is too slow, the surface stays tacky and pieces form twins. Twin formation ruins shape and also disrupts bed dynamics. Air temperature, airflow rate, and humidity are adjusted together to match spray volume, so every layer reaches a stable set before the next spray. As the shell thickens, the process shifts towards surface refinement. Spray amounts per cycle are reduced and drying time per cycle is increased. Thin syrup films flow into micro valleys, left by earlier growth, and smooth the texture. The drum motion can be adjusted slightly as hardness rises. Slightly higher rolling energy helps round edges once the shell can withstand impacts. The adjustment remains limited because impacts still cause chipping at rims. Color is built as a surface system rather than a single dye addition. Color solutions are mixed to precise concentration and filtered so no particles clog spray nozzles. Color is applied in multiple light coats, with full drying between coats. Light coats build saturation evenly and avoid pooling in low spots. Heavy coats would produce blotches because the shell surface is not perfectly smooth at the microscopic level. Color timing is selected to keep shade bright. If color is applied too early, it becomes buried under later clear layers and looks muted. If applied too late, it can sit on a very hard surface and show uneven adhesion. Many lines introduce color when shell thickness is near target, but before final smoothing coats are completed. Then a few clear coats are applied to lock pigment and improve durability. Color runs are typically separated by batch to prevent cross tint. The pan and spray lines are flushed between colors. The reason is not only appearance. Cross tint also affects quality checks because shade drift can mask surface defects. Optical color measurement compares sample pieces to target shade and drives adjustments in pass count or concentration. After color, the shell receives a final hardening sequence. Clear syrup layers are applied in very small volumes and dried with longer residence. This tightens the crystal structure near the surface and improves resistance to scuffing. Hardness is tied to moisture, so the process targets a defined moisture endpoint rather than simply drying as much as possible. Overdrying can make shells brittle and prone to chipping during conveying. Moisture equalization follows. Even when the surface is dry, the inner shell can hold slightly different moisture. Equalization holds the product in controlled air, so gradients flatten. This reduces internal stress that can create fine cracks, and it stabilizes the surface for polishing. Polishing creates gloss and improves flow. Pieces move to a polishing pan where motion is gentler. A polishing agent is applied as a fine mist in tiny doses. The pieces tumble and the film spreads across the surface through repeated contact. The film fills micro pores and reduces friction. Reduced friction lowers scuffing during packaging and improves hopper flow. Polish application is controlled because excess polish changes mouthfeel and can reduce color brightness. The process applies small additions followed by tumbling time to distribute evenly. A brief rest can follow, so the film sets and the surface becomes dry to the touch. Sorting and screening remove defects created during tumbling. Vibratory screens remove fines and broken chips. Optical systems can reject twins, chipped pieces, and off-shade pieces. Size classification can remove pieces outside the diameter band because off-size pieces roll differently and appear inconsistent in packs. The finished Smarties then feed packaging. Conveyors are designed with low drop heights and smooth curves because impact can chip shells. Hoppers are steep and low friction to prevent bridging. Multi-head weighers portion target weights by combining small hopper dumps. Stable flow depends on low dust and stable polish. 4. Bag formats. Portions drop into vertical form. Fill seal machines where film forms a tube and seals are made above and below the drop. Seal timing keeps pieces out of the seal area. For carton formats, weighed portions drop into cartons and cartons close by, tuck or glue. In either case, packaging materials are chosen to limit moisture transfer because moisture changes shell crunch and can cause sticking. Lindt chocolate is produced in a tightly structured factory process that begins with the transformation of raw cocoa beans into ultra-fine, smooth, and creamy chocolate using specialized machines, proprietary techniques, and finely tuned timing sequences that preserve the delicate flavors of cocoa while eliminating bitterness and grit. The process begins when whole dried cocoa beans arrive at the factory in large bulk containers and are conveyed directly into storage silos built to maintain low humidity and a stable temperature to prevent any premature oxidation or moisture absorption. From these silos, the beans are measured out by weight and directed into a cleaning unit where vibrating screens, air classifiers, and magnetic separators remove stones, dust, string, and any foreign matter so that only clean beans proceed to the next step. The cleaned cocoa beans are then transferred to a batch roaster or continuous drum roaster, which exposes them to dry hot air with precise temperature control and rotation speed to ensure the beans are heated evenly from all sides. Roasting develops the flavor of the cocoa, reduces astringency, and darkens the color of the nibs inside the shell. The temperature and duration of roasting are carefully controlled depending on the variety and origin of the bean, and are adjusted based on moisture content and desired flavor profile. Once roasted, the beans are cooled rapidly using forced air to prevent over-roasting, and then they move to the winnowing machine. The winnowing process cracks each roasted bean and separates the outer shell from the nibs inside. This is done using mechanical rollers that crush the beans gently, and blowers that blow away the lighter shells while heavier nibs fall into collection bins. The winnowed nibs are what contain the cocoa solids and cocoa butter required for chocolate production. These nibs are directed into large grinding chambers where rotating steel drums or stone rollers crush them into a thick, dark, gritty paste known as cocoa liquor. This liquor is then pumped into a series of high-pressure hydraulic presses that separate the fat from the solids. The fat becomes cocoa butter, while the remaining cake is pulverized into cocoa powder. In parallel, whole milk powder, sugar, and additional cocoa butter are stored in bulk hoppers and prepared to be added to the chocolate base. The exact formulation depends on whether the chocolate being made is milk, dark, or white. For milk chocolate, cocoa liquor is blended with sugar, milk powder, and cocoa butter in large horizontal mixers until a uniform paste forms. This coarse chocolate mass is then sent to the refining stage. Refining involves passing the chocolate paste through a sequence of steel rollers that reduce particle size. Each roller set progressively narrows the gap, crushing sugar crystals and milk particles until they are reduced to between 15 and 20 microns. This ultra-fine particle size is critical for the mouthfeel of Lindt chocolate, ensuring there is no graininess when the chocolate melts on the tongue. The refined chocolate then moves to the conching stage, which is one of the defining steps in Lindt production. Conching is done in elongated mixers called conches that slowly knead the chocolate at elevated temperatures, typically between 45 and 80 degrees Celsius, for several hours or even days, depending on the recipe. The purpose of conching is to develop flavor and texture. During this phase, volatile acids and off flavors are driven off by heat and agitation, while the friction created by the mixing reduces viscosity and smooths the fat dispersion. This stage also transforms the aroma profile, eliminating any lingering bitterness or sharp notes and rounding out the flavor. In Lindt's process, conching is considered both a science and an art, and the parameters are adjusted delicately to reflect the cocoa origin, sugar type, and desired smoothness. Once the chocolate mass has reached the optimal flavor and flow characteristics, it is transferred to tempering machines. Tempering is a controlled heating and cooling cycle that aligns the cocoa butter crystals into a stable form, known as form Vi. This ensures that the finished chocolate will have a glossy finish, a crisp snap, and will not develop bloom or grayish streaks over time. In the tempering machine, the chocolate is first heated above the melting point of all cocoa butter crystals, then cooled to a point where only form 5 can reform, and finally reheated slightly to working temperature. During this process, precise control of temperature and agitation is vital. Tempered chocolate is now ready for molding or enrobing. For bar production, tempered chocolate is poured into polycarbonate molds, which are vibrated on automated shakers to remove air bubbles and allow the chocolate to settle evenly into every corner. The molds are then passed through cooling tunnels, where cold air gradually lowers the chocolate temperature until it sets and solidifies. For filled chocolates or truffles, the molds may first receive a thin shell of chocolate, which is cooled and then filled with soft centers like ganache, praline, or liqueur before being sealed with more chocolate and cooled again. Once the chocolate has solidified, the molds are inverted and gently flexed by mechanical arms or vibration plates to release the bars or pieces. These are conveyed through a final inspection area where high-speed cameras and vision systems scan for imperfections such as broken corners, air pockets, or deformed logos. Defective. Pieces are rejected automatically, and perfect pieces proceed to wrapping. Wrapping is tailored to the product type. Lindt bars are typically wrapped in foil, followed by an outer paper sleeve. Machines cut foil to precise dimensions, fold it tightly around each bar, and then apply the paper wrapper using hot glue or pressure-sensitive rollers. Filled chocolates and balls are often wrapped in twisted foil ends or sealed flow packs using high-speed rotary packaging machines. Each wrapped unit is date-coded and batch-labeled for traceability. The wrapped chocolates are grouped into cartons by robotic arms that use suction cups to pick and place items into retail display boxes or shipping trays. Cartons are sealed, labeled, and palletized on automated stations where stretch wrap secures the load for transport. Pallets are scanned, assigned barcodes, and stored in climate-controlled warehouses to preserve flavor and appearance. The ambient temperature is maintained between 15 and 18 degrees Celsius with low humidity to prevent sugar or fat bloom from forming. Throughout the entire process, every parameter, from roast temperature to concha duration to tempering curve, is logged and monitored by a central control system. Inline sensors track viscosity, temperature, and particle size, while samples are pulled regularly for lab testing. These lab tests include moisture content, flow behavior, flavor analysis, and crystal structure confirmation to ensure the chocolate meets Lindt's quality standards. Chocolatiers also perform sensory evaluations, tasting samples for balance, aroma, melt, and finish. Hygiene and cleaning are equally critical in the production line. Chocolate making equipment is cleaned between product changes using melted cocoa butter flushes, which push out remnants of previous batches, followed by food-grade detergent cycles and high-pressure rinse systems. All cleaning is validated with swabs and lab tests to prevent flavor, cross-contamination, and microbial growth. In factories producing multiple chocolate types, changeovers are scheduled with precision to minimize downtime. Dark chocolate lines are usually run first, followed by milk, and then white chocolate, since darker varieties are more difficult to flush from equipment. Any chocolate not meeting specification during changeover is reworked or diverted to non-retail uses. Each ingredient in Lindt chocolate is treated with care. Sugar is milled to uniform crystal size and stored in dry silos with dehumidifiers. Milk powder is kept in oxygen barrier bags to preserve freshness. Cocoa butter is melted and filtered through fine mesh screens to remove impurities before blending. Even inclusions like nuts or fruit are roasted or candied on site to preserve their crunch and freshness. And they're added via gravity feeders that deposit precise amounts into the mold as chocolate flows in. The finished product that arrives on shelves results from a careful sequence where every gram of chocolate has passed through dozens of machines, heat cycles, mixing steps, and quality gates to guarantee it matches Lindt's profile for shine, snap, aroma, and flavor. From bean to bar, the chocolate moves with purpose through a network of conveyors, tanks, rollers, pumps, sensors, and skilled calibration, ensuring that what ends up in the foil wrapper is not just chocolate, but a refined and deliberate experience. Hershey's chocolate is manufactured through a large-scale factory process that transforms raw agricultural ingredients into solid molded chocolate bars, using a continuous sequence of heating mixing, refining conching, tempering molding, and packaging that is engineered for consistency, scale, and shelf life. The process begins with the intake of whole, dried fermented cocoa beans that are sourced in bulk and delivered in freight containers to the processing facility where they are offloaded using vacuum conveyors or bulk tipping systems into steel silos designed for moisture protection and temperature stabilization, so the beans are kept in ideal condition before production begins. From these silos, the beans are moved into a cleaning station where mechanical sieves, air separators, and magnetic traps remove foreign matter such as twigs, dust stones, and bits of string. And the cleaned beans then enter large batch roasters or continuous flow roasting drums where hot air is circulated through the rotating chamber to heat the beans evenly and activate the chemical changes responsible for chocolate flavor and aroma. The exact roasting temperature and time are carefully controlled to vary the flavor strength depending on the blend being produced, and the roasted beans are then cooled quickly using forced air or vacuum systems to lock in the desired profile and prevent overdevelopment. Next, the cooled roasted beans pass through a cracking and winnowing machine where roller blades break the shells apart, and airflow systems separate the lighter papery husks from the heavier cocoa nibs, which contain the actual cocoa solids and cocoa butter required for chocolate production. The separated nibs are collected and sent to grinding chambers, where heavy granite rollers or steel grinders crush them into a thick, dark paste known as chocolate liquor, which is not alcoholic, but simply refers to the pure ground state of cocoa solids suspended in their own fat. At this stage, the chocolate liquor is held in heated storage tanks, where it can be separated into cocoa butter and cocoa solids if necessary, using hydraulic presses or used directly in chocolate mass formulation. The chocolate base used for Hershey's milk chocolate typically includes chocolate liquor, sugar milk, powder, cocoa butter, and sometimes emulsifiers to improve flow properties. And in this stage, these raw materials are measured precisely using load cells and volumetric dosing systems before being transferred into industrial blenders, where they are mixed at high speeds into a coarse brown paste. The sugar crystals are still relatively large at this point, and the milk powder has not fully hydrated, so the mixture is lumpy and thick. But the goal of this step is to distribute the ingredients uniformly before refining. The refining process consists of passing the chocolate paste through a 5-roll mill or similar refining system, which crushes and shears the mixture repeatedly until all particles are reduced to between 15 and 20 microns in size, which is below the threshold of perception on the human tongue and is responsible for the smooth texture of finished chocolate. The refined powdery mass exits the rollers as dry flakes, which are collected and fed into large conching vessels, which are long horizontal mixers with heavy paddles that knead the chocolate continuously while applying gentle heat. Conching is one of the most important steps in the process and can last from several hours to a full day, depending on the batch size and the desired flavor characteristics. And during conching, the frictional heat softens the cocoa butter, allowing it to coat sugar and milk particles completely. While the mixing action evaporates unwanted volatile acids that contribute bitterness and also promotes chemical bonding between ingredients that gives chocolate its rounded flavor and creamy mouthfeel. In Hershey's process, this stage may include the addition of flavor compounds or the use of proprietary heating profiles that contribute to the distinctive, sweet, slightly tangy note associated with their milk chocolate. After conching, the now liquid chocolate mass is pumped through a fine mesh filter to remove any remaining solids, and then enters the tempering system, which is a temperature-controlled series of heat exchangers and holding tanks that bring the chocolate through a controlled heating and cooling cycle designed to stabilize the cocoa butter crystals into the desired form V structure, which provides gloss snap and resistance to fat bloom. The tempering process requires careful monitoring of viscosity temperature, shear rate, and time to produce a chocolate that will remain stable during storage and distribution. Once tempered, the chocolate is moved into the molding line, where it is dispensed into bar molds, using precise portioning heads that fill each cavity to the exact weight required. And the filled molds are shaken on vibrating tables to eliminate air bubbles and ensure even distribution of the chocolate across the mold. The molds then pass through a cooling tunnel where refrigerated air is circulated in stages to gradually bring the chocolate down to the release temperature, allowing it to solidify without developing stress cracks or surface bloom. When the chocolate has fully set, the molds are inverted and the bars are ejected using mechanical arms or flexing systems that pop the finished bars onto conveyor belts for inspection. Every bar passes under a series of vision systems that scan for surface defects, broken edges, misaligned logos, or irregular thickness, and any bar that fails inspection is automatically diverted for rework. Acceptable bars move forward to the wrapping section, where high-speed machines fold foil or film around each piece and seal it using heat or pressure depending on the packaging format. Paper sleeves or cardboard cartons are then applied and printed with product information barcodes and expiration dates using inline inkjet or laser printers. Wrapped bars are grouped into shipping cases by robotic packing arms and loaded onto pallets, which are stretch wrapped and labeled for traceability before being moved into temperature-controlled storage rooms maintained between 15 and 20 degrees Celsius to preserve texture and flavor. From this point, the bars are distributed through refrigerated trucks or ambient carriers depending on shelf life and destination requirements. In parallel with production, the entire process is monitored by sensors that record key data at every stage, from ingredient weight and tank temperature to roller pressure and mold cavity fill speed. And this data is fed into a centralized quality control platform that logs all production variables and triggers alerts if any parameter drifts outside the approved range. Quality assurance teams sample bars from each batch and test them in laboratories for moisture content, melt profile, flavor, strength, hardness, and microbiological stability. And these tests ensure that every bar maintains the same quality level regardless of where or when it is produced. All equipment used in the chocolate production line is constructed from food-grade stainless steel and is subject to strict sanitation protocols between product runs. Clean-in-place systems flush liquid chocolate from pipes and tanks using melted cocoa butter, followed by hot detergent solutions and sterile water rinses, and these cleaning cycles are verified using swab tests and microbial analysis before the next production run begins. During cleaning, mechanical components such as belts, pumps, and seals are inspected for wear and lubricated with food-safe oils to maintain performance and prevent contamination. Because Hershey produces multiple chocolate types, including dark white and flavored variants, the factory must perform regular changeovers that are scheduled with precision to minimize waste and avoid flavor crossover. And this is typically done by running from the lightest product to the darkest, so that any residual ingredients are less likely to impact flavor in the next batch. Storage of ingredients is just as critical as processing, and milk powder is kept in dehumidified silos lined with oxygen barriers, while cocoa butter is stored in heated jacketed tanks that maintain a constant liquid state, and sugar is held in dry bins fitted with vibratory feeders to ensure consistent flow into the mixers. Even inclusions like almond toffee or cookie pieces are added through dedicated feeders designed to introduce solids at the molding stage without disrupting flow or causing jams. From beginning to end, Hershey's chocolate production line is a finely tuned balance of mechanical engineering, food science, and sensory evaluation, where the transformation of beans into bars depends on maintaining strict control over texture, flavor, and structural integrity. The iconic bars that result are the outcome of thermal history particle refinement, fat crystallization, and packaging precision that together produce a chocolate that is consistent across millions of units and recognized by consumers around the world. Godiva chocolate production begins with the careful handling of raw cocoa beans, which arrive at the factory in bulk loads from cocoa growing regions and are stored in cool, dry silos that prevent moisture contamination, oxidation, and pest activity. These beans are first cleaned through mechanical sifters that remove stone shells dust and organic debris using a series of vibrating screens, suction fans, and magnetic traps. Once cleaned, the beans are weighed and portioned by automated systems and conveyed to the roasting chambers, which are precision-engineered rotating drums capable of uniform thermal penetration across the entire mass of cocoa beans. Roasting is the first flavor-developing stage in the chocolate-making process, and in the Godiva production method, it is carried out at moderate temperatures for extended periods, which helps preserve the aromatic volatiles while driving off unwanted acidity and bitterness. Each batch is roasted based on its origin and moisture level, with constant temperature regulation using internal thermocouples that feed data to a computerized control system. Once the beans are fully roasted, they are immediately cooled with forced air systems that halt the roasting curve and stabilize the volatile compounds formed during heating. The next step is winnowing, which involves cracking the roasted beans open to separate the brittle shells from the cocoa nibs inside. The beans pass through a mechanical cracker that gently fractures them, and a pneumatic winnower that blows the lighter shells away while the heavier nibs fall into collection bins. These nibs are the core ingredient in all chocolate and contain both cocoa solids and cocoa butter in their natural ratio. The nibs are routed to a pre-grinding unit where rotating stone rollers or steel discs crush them into a thick, gritty paste known as cocoa liquor. This liquor is heated slightly to reduce viscosity and then transferred to high-pressure hydraulic presses that squeeze out the cocoa butter, leaving behind a dense cake of compressed solids which are ground into cocoa powder. For milk chocolate production, the cocoa liquor is blended with refined sugar, high-quality milk powder, additional cocoa butter, and in some recipes, a hint of vanilla or lecithin, which acts as an emulsifier. Each ingredient is dosed using gravimetric feeders and poured into large, high-speed mixers where they are combined into a smooth, uniform brown paste. This initial chocolate mass is far too coarse to be palatable, so it is sent to the refining system. This consists of a 5-roll mill where the mixture passes between sets of rollers that progressively reduce the particle size down to below 20 microns, creating a texture that feels smooth and creamy on the tongue. After refining, the powdered chocolate mass is transferred into conching machines, which are large horizontal vessels with internal mixing blades that work the chocolate slowly while applying gentle heat. This process can take anywhere from 12 to 24 hours, depending on the desired flavor profile, and is critical for developing the smooth texture, deep aroma, and balanced flavor that distinguishes Godiva from other mass-market chocolates. The conching action evaporates undesirable acids and moisture while distributing the cocoa butter evenly over every particle, which contributes to the distinctive mouthfeel and melt of the final product. Once conching is complete, the chocolate is sent through a filtration unit to remove any remaining impurities and then proceeds to the tempering stage, which is one of the most technically precise parts of the entire process. Tempering involves heating the chocolate to above its melting point, then cooling it down to initiate the formation of stable cocoa butter crystals known as Form 5, and then slightly reheating it to a working temperature, where those crystals can be maintained in suspension. This controlled crystallization ensures that the finished chocolate will have a glossy sheen, a crisp snap when broken, and a long shelf life without the development of sugar or fat bloom. The entire tempering process is carried out in enclosed stainless steel tanks equipped with agitators and digital thermostats that keep the temperature profile exactly within a 1-degree tolerance. The tempered chocolate is now ready for molding or enrobing. For solid chocolate bars or shapes, the tempered chocolate is poured into precision-engineered molds made of food-grade polycarbonate. These molds are vibrated to remove air bubbles and ensure that the chocolate spreads evenly into every corner and detail of the design. The filled molds then pass through a cooling tunnel that gradually lowers the temperature, allowing the chocolate to solidify and contract slightly so it can release cleanly from the mold. The pieces are then turned out and conveyed to the packaging line. For filled chocolates like pralines, truffles, and caramels, the process adds additional steps. The mold is first coated with a thin layer of tempered chocolate using spinning or tilting mechanisms to create a uniform shell. This shell is cooled just enough to firm up and then filled with liquid centers like ganache hazelnut paste or fruit cream using precision nozzles that deliver exact volumes to each cavity. Once filled, the chocolates are sealed with a final layer of chocolate and sent through a second cooling tunnel to solidify completely. These filled chocolates are then demolded and sent to wrapping. Enrobed chocolates, such as chocolate-covered nuts or biscuits, are passed on a conveyor belt under a waterfall of tempered chocolate where they are coated completely and pass under a vibrating plate that ensures even coverage and allows excess chocolate to drip off. The enrobed pieces then pass through a cooling tunnel similar to the molded chocolates where the coating solidifies uniformly. Wrapping is carried out using high-speed automated systems that use foil or flow wrap depending on the product. Each chocolate is first wrapped in an inner layer to preserve freshness and then given an outer wrap or box depending on whether it's a single piece or part of a collection. These wrappers are applied using thermal sealers and folded precisely by mechanical arms to maintain presentation quality. The finished chocolates are grouped into assortments using pick-and-place robots that load them into rigid trays or decorative boxes, which are then closed, labeled, and shrink-wrapped for transport. Throughout the entire production process, quality control is integrated into every stage. Inline sensors measure parameters like particle size, viscosity temperature, and moisture content. Random samples are taken and tested for flavor consistency, flow behavior, microbiological safety, and visual appearance. Each batch is tracked from bean to box using barcode systems and digital batch records, which allow full traceability and accountability. Any deviation from the strict specifications results in automatic rejection and investigation to maintain the high quality associated with Godiva. Packaging lines are designed not only for speed, but also for delicate handling. Chocolates are not simply dropped into boxes, but placed gently by grippers or vacuum arms to prevent any scuffing or deformation. Seasonal and limited edition boxes are assembled by dedicated packaging stations that include decorative inserts, gold leafing, or ribbon application, all of which are coordinated with the central production database to match inventory with demand forecasts. Finished products are palletized automatically and moved to cold storage areas where the ambient temperature is held between 15 and 18 degrees Celsius with low humidity to protect against fat bloom sugar crystallization or flavor degradation. Logistics systems monitor inventory in real time and coordinate dispatch using climate-controlled vehicles that ensure the chocolates arrive at retail destinations in pristine condition. Factory sanitation is handled with clean-in-place systems for all enclosed equipment and rigorous manual cleaning protocols for all external surfaces. Between product types, especially when transitioning from dark to milk or white chocolate lines, are flushed with cocoa butter and inspected using allergen tests to confirm no cross-contamination occurs. Equipment such as molds tempering tanks and piping is made from food-grade stainless steel and is subject to frequent validation, including swab tests, microbiological plating, and ATP analysis. Each product that leaves the factory reflects a meticulously controlled combination of mechanical design, sensory expertise, thermal precision, and ingredient handling, all executed on a scale that allows handcrafted quality to meet global demand. Godiva's reputation depends on this balance where artistry meets automation, where every bar and truffle is not only shaped by steel and steam, but guided by formulas and feedback that ensure every box offers the same refined, luxurious experience no matter where it is opened. The process for Snickers peanut butter begins with the receipt and inspection of raw materials, including roasted peanuts, refined sugar, corn syrup, dextrose, hydrogenated vegetable oil, skimmed milk solids, cocoa liquor, cocoa butter, soy lecithin, salt, egg white solids, lactose, whey, and artificial flavors. Each ingredient is stored in designated silos or temperature-controlled containers depending on its physical state. Dry powders are handled in gravity-fed bins, while oils and syrups are stored in jacketed tanks with agitation and temperature control to maintain fluidity. Peanuts used in the formulation are first screened for foreign matter using rotary sieves and magnetic separators, then conveyed into buffer hoppers feeding a roller mill that cracks them into uniform granules. The granulated peanuts are then pneumatically transferred to storage silos for batch-based dispensing into the peanut butter blend. The peanut butter layer is produced in a batch mixing system where peanut granules are combined with vegetable oil, sugar, salt, and stabilizers in a ribbon blender with temperature regulation. The mixture is homogenized using a high shear inline mixer and heated to 48 to 52 degrees Celsius to achieve pumpable viscosity. The finished peanut butter is stored in jacketed holding tanks equipped with level sensors and recirculation loops to prevent phase separation. The nougat layer is prepared using a continuous aeration system. Corn syrup, sugar, and water are cooked in a steam-jacketed vessel to 120 C, 120 degrees, and transferred to an aerator, where air is whipped into the syrup, along with milk solids, egg white solids, and stabilizers. The result is a light, aerated nougat with controlled density between 0.35 and 0.45 GC/Sec-M3. The nougat is extruded through a calibrated nozzle system onto a continuously moving cooling belt lined with a polyethylene release film. The nougat band is cooled to below 20 degrees Celsius using overhead chillers and bottom surface cold plates. Once cooled, a uniform layer of peanut butter is deposited onto the surface using a curtain depositor. The thickness of this layer is maintained using servo-controlled doctor blades. Viscosity and temperature of the peanut butter are constantly monitored by inline viscometers and thermocouples, with feedback loops adjusting jacket temperature and pump speed. A caramel layer is prepared by cooking sugar, glucose syrup, milk solids, and fats to a target temperature of 115 to 118 degrees, followed by emulsification in a vacuum mixer to remove air bubbles. The caramel is applied as a third layer over the peanut butter using a heated roller spreader system with a calibrated gap to ensure uniform layer thickness. The caramel is cooled rapidly using forced air and chilled roller contact to reach slicing firmness. The tri-layer slab, consisting of nougat, peanut butter, and caramel, is conveyed through a compaction system consisting of top and bottom pressure belts to eliminate internal air pockets and ensure structural uniformity. The slab then enters the slitter station, where rotary knives cut it longitudinally into lanes matching the final bar width. Each blade is aligned using digital edge sensors to maintain cutting accuracy within plus or 0.5 millimeters. The individual lanes are separated using diverging conveyors and conveyed into the guillotine cutter, where servo-driven blades slice the moving slab into individual bar lengths, typically 38 to 52 grams per unit. Cut bars are spaced automatically using smart belts that adjust speed based on line accumulation to prevent product overlap and damage. Any misshaped or undersized bars are rejected using pneumatic knockoff arms. Bars proceed to the enrobing station, where they pass under a waterfall curtain of tempered milk chocolate. The chocolate is maintained at 30 BSDRs and has a viscosity range of 1,800 to 2,200 centipoise. A vibrating wire mesh belt ensures uniform base coverage, while an air knife blows off excess chocolate from the top and sides. Enrobed bars are passed through a vibrating section to settle the coating and remove trapped air. The enrobed bars enter a cooling tunnel divided into progressive zones starting at 10 degrees C and gradually increasing to 16 degrees C to prevent fat bloom and cracking. Tunnel length is approximately 30 to 40 meters, with dwell time ranging from 5 to 8 minutes depending on coating thickness and line speed. Product core and coating surface temperatures are measured at tunnel exit to confirm stabilization below 20 degrees C. Post-cooling, bars are inspected using machine vision systems that assess enrobing quality, dimensional conformity, and surface defects such as bubbles or incomplete coverage. Rejected units are logged by defect type and removed automatically. Accepted bars continue to the packaging line, where they are fed into a flow wrapper via vibratory lanes and pocket conveyors that align them to wrapping speed. Wrapping film is fed from a roll and registered using optical mark sensors. The film is formed into a tube around each bar using a forming box. Longitudinal seams are sealed by rotary heat seal wheels, and end seals are created by jaw sealers operating at 135-150 degrees C. Barcodes and date codes are printed in line using thermal transfer printers. Film tension, seal temperature, and print registration are continuously monitored by the wrapper PLC. Wrapped bars are weighed using in-motion check weighers with a resolution of 0.1 grams. Any bars outside the tolerance band are ejected using pneumatic side gates. Accepted bars are collated into groups by rotary collators and packed into folding cartons by robotic pick-and-place systems using vacuum cups. Cartons are erected, filled, and sealed with hot melt adhesive applied by contact nozzles. Cartons are verified by weight and barcode before being conveyed to case packing. Case packing involves grouping cartons into shipping cases that are erected and sealed by automated case erectors and tapers. Cases are labeled using thermal inkjet or print and apply labelers and stacked onto pallets using robotic arms with end effectors configured for the case size. Pallets are wrapped with stretch film and labeled with pallet license plates that include batch number, product code, production line, and timestamp. Finished pallets are stored in temperature-controlled warehousing environments between 18-20 C2 degrees and 50-60% RH. Warehouse Management Systems, WMS, use barcode scanning to log pallet locations and ensure FIFO inventory management. Distribution occurs through cold chain logistics to ensure product quality during transportation. Each process step is monitored and controlled using a supervisory control and data acquisition SCADA system that collects data from sensors, scales, thermocouples, and flow meters across all stages. This data is displayed on human-machine interfaces, HMIs, for line operators and stored in batch records for traceability. Any deviation from standard parameters triggers alarms and corrective actions. Allergen segregation protocols are enforced at every stage. Peanut and milk processing areas are physically segregated. Equipment used for peanut butter and chocolate are color-coded and cleaned separately. Swab testing for protein residues is conducted after cleaning and before changeovers. Cleaning validation includes visual inspection, chemical residue tests, and microbial swabbing. Preventive maintenance schedules for all equipment are based on run hours or production cycles. Components such as chocolate pumps, depositor nozzles, cutter blades, belt rollers, and sealing jaws are inspected and replaced as needed. Maintenance activities are logged in a computerized maintenance management system, CMMS, which alerts engineering teams when parts reach predefined wear thresholds. Quality control includes hourly sampling of bars for destructive testing. Tests include measurement of bar weight, length, width, height, chocolate shell thickness, peanut distribution, and filling ratio. Moisture content is tested using rapid moisture analyzers, while texture is measured using texture profile analysis, TPA, machines. Sensory testing is performed by trained panelists in isolated booths with controlled lighting and ventilation. Shelf life studies are conducted by storing finished products under accelerated and ambient conditions. Parameters tested include moisture migration, lipid oxidation, microbial stability, chocolate bloom, and filling separation. Results are used to validate expiration dates printed on each unit. Finished goods are subject to audit by internal QA and external certification bodies to ensure compliance with food safety standards. All production, inspection, and packaging records are stored electronically and can be retrieved instantly for traceability. Raw material lot numbers are linked to final product batch codes, allowing for upstream and downstream tracking in case of complaints or recalls. Root cause analysis is performed for any non-conformance, with results reviewed in monthly quality audits. M&M's caramel candies are manufactured through a multi-stage process that includes caramel cooking and forming, caramel center pre-coating, chocolate panning, hard shell sugar coating, polishing, sorting, inspection, and packaging. Each of these stages is optimized for continuous production and strict dimensional and weight tolerances. The process begins with preparation of the caramel center using industrial cooking vessels equipped with direct steam injection and mechanical agitation. A mixture of glucose syrup, refined white sugar, sweetened condensed milk, palm oil, emulsifiers, salt, and natural flavoring is pumped into the batch cooker. The initial ingredients are metered by mass flow meters and load cells to ensure precise ratio control, typically with a solids concentration exceeding 85% in the final cooked mass. Cooking is conducted at temperatures between 115 degrees Celsius and 120 degrees Celsius, and continuous agitation prevents scorching and ensures homogeneous heating. A vacuum step may be applied after atmospheric cooking to reduce moisture content without exceeding target temperatures, improving chew texture and shelf stability. Once the required consistency is reached, the caramel is transferred to a cooling table or cooling drum equipped with scraper arms, which reduce the mass temperature to below 50 degrees Celsius and prepare it for forming. The cooled caramel mass is sheeted and cut using a rotary cutter and high-precision die system. The sheeted caramel slab is passed through gauge rollers to reduce thickness and fed into a rotary die-cutting unit where small square or rectangular cores are punched out. The cutting system operates in synchronized alignment with the conveyor speed to avoid misshaping. Each core is formed to within plus T 0.2 mm of the target dimensions, and cut weights are maintained at 2 to 3 grams per center depending on final candy size. After cutting, the caramel centers are conveyed to a pre-coating drum where they are tumbled with a fine mist of modified starch or food-grade wax. This stage prevents sticking and prepares the surface for chocolate adhesion. The pre-coated caramel pieces are temporarily stored in stainless steel bins under humidity-controlled conditions with less than 40% RH before being transferred to the chocolate panning units. Chocolate coating is conducted in automated panning drums with oscillating movement and programmable dosing cycles. Each pan receives a calibrated quantity of caramel centers and begins rotation at 18 to 24 RPM. Tempered milk chocolate is sprayed onto the tumbling centers in controlled quantities through heated nozzles. Each chocolate application is followed by a cooling phase using dehumidified cold air injection to solidify the layer before the next application. This chocolate build-up cycle continues for multiple iterations until the centers reach the specified chocolate layer thickness. Sensors within the panning unit monitor temperature, humidity, and drum load to prevent agglomeration or flattening. The total chocolate coating phase typically lasts 60 to 90 minutes, depending on desired shell thickness and line speed. By the end of this stage, each center is fully encapsulated in chocolate and cooled to under 25 degrees Celsius before proceeding to the sugar coating line. Sugar coating or hard panning is performed in high-capacity rotating pans with batch sizes ranging from 300 to 600 kilograms. A mixture of sucrose, glucose syrup, water, colorant, and titanium dioxide is sprayed in layers onto the chocolate-coated centers. The initial applications are made with higher syrup content to ensure adhesion and are followed by increasingly dry applications to harden the shell. Between each application, cold air is blown into the pan to crystallize the syrup and lock the layer in place. The coating is built in 20 to 40 layers, with rotation speed, syrup flow rate, and airflow rate adjusted in real time by PLC-controlled systems. Specific gravimetric dosing pumps ensure each batch receives a uniform mass of syrup and colorant. Standard M&M's caramel products are colored using a fixed ratio of FDA-approved colorants, with pan scheduling arranged to avoid cross-color contamination. Each color batch is tracked with a unique identifier linked to its dye lot and pan ID. As the sugar shell builds, the product passes through a smoothing phase where the surface is hydrated and then gently polished with microcrystalline wax. This polishing provides the final product with its gloss and protective coating. A final tumbling phase is conducted in pans lined with polishing baffles and anti-static systems to prevent buildup on the interior walls and ensure free movement of the candies. After polishing, M&M's caramel units are conveyed to the grading station. A multi-tiered vibratory grading system separates any units that deviate from size specifications. Grading is followed by weight sorting, using high-speed check weighers capable of scanning up to 300 units per minute. Acceptable candies fall within a defined weight range. Over- and underweight items are automatically rejected and logged by defect code. Product inspection follows. Each candy passes through a vision system using a series of high-resolution cameras and 360-degree rotation to check for shell defects, discoloration, incorrect sizing, and incomplete polish. Any non-compliant unit is removed from there, streamed via pneumatic nozzles, and collected in segregated bins. Rejected items are logged and analyzed for trends in production issues, triggering upstream corrective actions if thresholds are exceeded. Accepted product is conveyed to the packaging system, where candies are temporarily stored in surge hoppers with level sensors to buffer production flow. Product is dosed using multi-head combination weighers that calculate the optimal combination of candies to achieve target package weights, typically 34 to 80 grams, depending on SKU. Weigher buckets are constructed of low-friction stainless steel and cleaned regularly to prevent flavor, carryover, or build-up. Filled product drops into vertical form-fill seal machines, where printed laminate film is formed into a pouch, filled, and sealed with constant heat seal bars. Seal integrity is verified using pressure sensors and thermographic imaging. A nitrogen flush is applied before sealing to reduce oxygen levels inside the pouch, thereby enhancing shelf life. Packages are printed with production code, best by date, line number, and timestamp using continuous inkjet printers. Sealed pouches are conveyed to check weighers for final weight verification and then pass through metal detectors set to detect ferrous, non-ferrous, and stainless steel contaminants. Any off-weight or contaminated package is rejected. Accepted packages are collated into larger trays or cartons using pick-and-place robotic arms equipped with vacuum grippers. Cartons are assembled, filled, and sealed using hot melt adhesive and barcode labels applied on the side panel. Shipping cartons are scanned and aggregated onto pallets using automatic palletizers that form specific stacking patterns for warehouse efficiency. Each pallet is wrapped with stretch film and labeled with pallet-level tracking codes tied to the plant's manufacturing execution system. Pallets are transferred to a finished goods warehouse where temperature is maintained at 18 to 20 degrees and humidity is kept under 60% RH to protect product quality. Quality assurance sampling occurs every 15 to 30 minutes at critical control points. Samples are taken from post-coating, post-polishing, and final package stages. Laboratory tests include moisture analysis via halogen, moisture analyzers, shell thickness measurement with micrometers, coating adhesion tests, drop impact testing for shell integrity, and taste panel validation. Shelf life studies are conducted on retained samples stored at standard and accelerated aging conditions. Cleaning and sanitization are conducted on a rotating schedule. Chocolate and caramel handling areas undergo full CIP, clean-in-place procedures involving hot alkaline solutions, acid rinses, and sterile water flushes. Sugar panning and polishing pans are dry cleaned using brushes, vacuum systems, and compressed air. Contact surfaces are swabbed for microbial residues, and test results are logged digitally for traceability. Allergen control is strictly enforced. Caramel and chocolate processes containing dairy and soy are segregated. Line clearance protocols require full removal of previous ingredients, verified by visual inspection and protein swab testing before new production begins. Changeovers are validated with QA sign-off. Batch tracking is implemented through digital batch records containing ingredient lots, process parameters, equipment settings, cleaning records, operator IDs, inspection results, and deviation logs. Any deviation from specification limits requires root cause analysis and corrective action under documented quality systems. Rework from rejected product is limited and processed only after evaluation of safety and quality impact. Preventive maintenance occurs based on machine runtime hours. Key systems like chocolate pumps, coating nozzles, panning motors, weighing buckets, and forming jaws are monitored for wear and replaced proactively. Predictive diagnostics include vibration analysis and temperature monitoring of motor bearings, and these readings are stored in a central database for long-term equipment performance tracking. The production of Twix White begins with the synchronized preparation of three main structural components: the shortbread biscuit base, the caramel layer, and the white chocolate coating. Each component is manufactured in separate sublines within the facility and converges later during the bar forming phase. The process starts with the biscuit base. Refined wheat flour, invert sugar syrup, vegetable shortening, powdered milk, salt, and leavening agents are dispensed into a horizontal planetary mixer. Dry ingredients are fed from bulk storage silos through gravity chutes or pneumatic lines, each portion controlled by weigh batches to an accuracy of plus watt boige 1%. Liquid components are pumped from heated jacketed tanks and injected through metered valves. The mixing cycle includes 2 stages: dry blending for even distribution of powders, followed by wet incorporation using medium speed agitation. The dough is formed to a target moisture content between 16 to 18% to ensure optimal flow and shaping characteristics. Upon completion, the dough is conveyed via a stainless steel auger system to a rotary molder. In the rotary molding station, the dough is formed into uniform, rectangular shortbread fingers. The molder consists of a rotating drum engraved with bar-shaped cavities and a compression roller. Dough is pressed into these cavities as the drum rotates over a steel forming plate. Excess dough is scraped off by a doctor blade and recirculated back into the feed system. The molded dough pieces drop onto a perforated baking belt made of food-grade stainless steel mesh. The formed biscuit bases enter a continuous tunnel oven with multiple heating zones. Each zone uses indirect gas-fired heat or electric radiant panels to maintain a gradient from 180 degrees Celsius at the entrance to 220 degrees Celsius in the final zones. The baking time ranges between 8 to 10 minutes. Infrared sensors monitor surface temperatures, while dew point sensors control internal humidity. The goal is to fully gelatinize the starch, set the structure, and reduce internal moisture content to below 3.5%. After baking, the biscuits are transferred to a mesh cooling conveyor where ambient air is forced from both above and below using axial fans. Surface temperature is reduced to under 30 degrees before the biscuits are sent downstream. During this phase, any misshaped or cracked bases are automatically rejected using laser sensors and high-speed diverters. Parallel to biscuit preparation, caramel is cooked in a steam-jacketed stainless steel cooker equipped with a vacuum system. The caramel mixture consists of glucose syrup, refined sugar, sweetened condensed milk, vegetable fat, and emulsifiers. The blend is heated to between 115 degrees CS and 120 degrees CS under continuous agitation to achieve a homogeneous, smooth consistency. A vacuum stage follows to reduce moisture content and prevent Maillard browning beyond the desired level. Once cooked, the caramel is pumped through an inline cooler, reducing its temperature to 50 or 55 degrees Celsius and fed into a pressurized buffer tank. The caramel is held under constant agitation to prevent crystallization and separation. It is then transferred to a curtain depositor located above the biscuit lines. Each biscuit base moves underneath the depositor at synchronized speeds, where a layer of caramel approximately 3 to 5 mm thick is dispensed onto the center. The caramel-coated biscuits proceed to the chilling tunnel, which operates between 5 degrees Celsius and 8 degrees Celsius, with controlled air velocity and laminar flow. This section ensures the caramel firms to a semi-solid state, allowing the bars to retain shape during subsequent handling. Cooling dwell time is carefully controlled to prevent cracking or internal condensation. Next is the enrobing process. White chocolate coating is prepared by melting white compound chocolate composed of sugar, milk solids, cocoa butter alternatives, and lecithin. It is stored in heated tanks, maintained at 42-45 degrees Celsius. The chocolate is filtered to remove particulate matter and pumped into the enrober. Each caramel-topped biscuit is conveyed through a waterfall curtain of white chocolate. The enrober consists of a chocolate pump, curtain plate, bottoming pan, and vibrating removal section. The base of each bar contacts a submersion roller to ensure full underside coverage. A vibrating wire belt helps distribute the chocolate evenly, while an air knife system positioned immediately after the curtain blows excess chocolate off the top and sides to maintain uniform shell thickness. The enrobed bars enter a cooling tunnel set to 10 to 14 degrees. The tunnel is 20 to 30 meters long and provides 3 and 6 minutes of cooling time. The goal is to solidify the chocolate coating to a firm, glossy finish without causing thermal shock or shell fractures. Airflow patterns and tunnel humidity are tightly regulated to prevent surface bloom and condensation. Upon exit, bars pass through a vision inspection system. High-resolution cameras capture top, side, and bottom views. Pattern recognition software detects coating voids, caramel leaks, surface cracks, and dimensional anomalies. Bars not conforming to target specifications are removed via pneumatically controlled ejectors and collected in reject bins for offline evaluation. Compliant bars are transferred to the primary packaging line. Bars are individually flow wrapped using printed multi-layer laminate films. The film is drawn over a forming collar and sealed using horizontal sealing jaws, operating at 135-145 degrees C. Before the end seal is applied, a nitrogen flush displaces oxygen within the wrapper to preserve product freshness and extend shelf life. A thermal inkjet printer marks each wrapper with a date code, lot number, and timestamp synchronized with the manufacturing execution system. Sealed bars are conveyed through metal detectors calibrated for stainless steel and ferrous particles at sensitivities below 1.5 mm. Packages outside weight or contaminant parameters are ejected and logged. Wrapped units are collected into collators that form groups for secondary packaging. Robotic pick-and-place systems use vacuum grippers to load bars into pre-formed cartons or trays. Cartons are closed using hot melt glue, and barcodes are printed for traceability. Completed cartons are conveyed to automated case packers. Shipping cases are assembled, filled, and sealed using tape or adhesive. Each case is labeled with a shipping code, pallet code, and production metadata. Palletizing robots stack cases according to predefined patterns. Pallets are stretch wrapped and scanned before being stored in the finished goods warehouse, which maintains ambient temperatures of 18 to 20 degrees and relative humidity under 60%. Each bar produced is tied to a batch number through digital production records, including all ingredient lot numbers, mixing parameters, baking temperatures, caramel cooking data, enrobing flow rates, cooling dwell times, and packaging specifications. These records are accessible for traceability, audits, and regulatory compliance. Routine inline quality control includes sampling from every production hour. Samples are weighed, measured, and evaluated for coating thickness, layer adhesion, caramel placement, and hardness using calibrated micrometers and texture analyzers. Moisture content is verified using halogen moisture balancers, and chocolate temper is tested with temper meters to confirm crystallization profiles. Laboratory testing also includes water activity analysis, fat bloom resistance, and accelerated shelf life testing under elevated temperature and humidity conditions. Results are logged in a quality database and reviewed by technical managers during shift changes and weekly audits. Sanitation of the line is scheduled daily and weekly depending on the zone. Dry cleaning is applied to the biscuit molding and baking lines using brushes and compressed air. Wet cleaning is used on caramel and chocolate zones, involving hot water rinses, food-safe alkaline detergents, acid neutralizers, and sanitizer sprays. Enrober parts are disassembled and cleaned using CIP-compatible tanks. Allergen management involves physical segregation of peanut, tree nut, and dairy-containing ingredients. Changeovers require full clean-out of product contact surfaces and verification using allergen-specific protein swab kits. If protein residue exceeds defined thresholds, equipment is re-cleaned until test values fall within limits. All material movement, from raw ingredient delivery to palletized product dispatch, is tracked using barcodes and integrated into the facility's ERP and SCADA systems. These systems enable real-time monitoring of production rates, downtime, line efficiency, scrap rates, and output per shift. Alarm logs, deviation reports, and maintenance requests are automatically archived for compliance purposes. Preventive maintenance schedules cover all rotating equipment, pumps, cooling compressors, depositor heads, vibratory conveyors, belt motors, and sealing modules. Wear parts such as blades, nozzles, bearings, belts, and gaskets are replaced at specified run-hour intervals. Predictive analytics using vibration sensors and thermal imaging assist in identifying failure risks before downtime occurs. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled, so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming, so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming, so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or Sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing, the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the R sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed, so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. Water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. Proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources such as vegetable oil or butter are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix. The process begins with the reception of raw cacao beans. These arrive in large burlap sacks, which are automatically tipped into a stainless steel hopper. The hopper feeds a vibratory conveyor, shaking the beans in a controlled rhythm to remove debris and small stones. As the beans travel, high-powered magnets and air jets eliminate metallic fragments and lighter contaminants. Once cleaned, the beans move into the roasting chamber. This is a horizontal, drum-style roaster with precise temperature zones along its length. The beans are roasted between 120 degrees Celsius and 150 degrees Celsius for 30 to 45 minutes, depending on origin and moisture content. Inside the rotating drum, baffles lift and drop the beans repeatedly to ensure even exposure to heat. The surface crackles as volatile acids are driven off, and the aroma intensifies. Roasting profiles are strictly controlled using infrared sensors and thermal probes. After roasting, the beans exit into a rapid cooling system, a double-jacketed air cooling tunnel that quickly brings the temperature down to prevent over-roasting. As the beans cool, they're conveyed to the winnowing station. Here, a precision cracking roller gently fractures the outer shells. The mixture then passes through an ascending air column. Shells, being lighter, are blown upward and extracted into a cyclone separator. The heavier nibs fall downward, separated cleanly. The nibs are then routed into the liquor grinding system. This involves a two-stage reduction process. First, a coarse grinder reduces the nibs into a paste-like mass using granite rollers. This mass, still gritty, feeds into a 5-roll refiner. The rolls are made from hardened steel and arranged in descending gap widths. The rollers spin at increasing speeds to shear the particles down to 20 microns. During this stage, the paste becomes smooth and glossy, now known as chocolate liquor. From the refiner, the liquor is pumped into a conching machine. This is a long, horizontal tank with heavy granite paddles. The paddles rotate slowly but forcefully, kneading the liquor for up to 72 hours. During this process, frictional heat raises the temperature to 50-60 degrees Celsius. This drives off unwanted volatiles and enhances texture. As it churns, the chocolate undergoes subtle flavor transformation and becomes fluid, velvety, and aerated. At this stage, additional ingredients are introduced through precision feeders. Sugar is added via a sealed screw conveyor that meters crystalline particles in carefully measured doses. Milk powder, if producing milk chocolate, is pre-blended with a small portion of cocoa butter before being added. The mix is tested repeatedly with inline viscometers and particle size analyzers to ensure consistency. Next, the chocolate moves into the tempering system. This consists of 3 stainless steel heat exchangers that rapidly cycle the chocolate through defined temperature curves. The liquid chocolate is cooled from 45 degrees Celsius down to around 27 degrees Celsius and then reheated to 31 or 32 degrees Celsius. This carefully controlled crystallization process encourages the formation of stable cocoa butter crystals, Form 5, which gives the final chocolate a glossy finish and crisp snap. Once tempered, the chocolate is ready for molding. It flows into automated depositor heads mounted above polycarbonate molds. Each head features multiple precision nozzles controlled by servo motors. The nozzles deposit exact volumes of chocolate into the cavities, synchronized with the moving mold belt below. Vibration tables mounted beneath the molds shake rapidly, eliminating trapped air and evening out the surface. The molds enter a cooling tunnel, a refrigerated corridor where temperature and humidity are tightly regulated. Inside, a chilled airflow passes over the molds for 10 to 15 minutes, bringing the chocolate down to 8-10 degrees Celsius. This solidifies the product and locks in the tempered structure. Once cooled, the molds are inverted and gently flexed by mechanical arms to release the solid chocolates. They drop onto a food-grade conveyor belt, which directs them to the decorating and enrobing section. Here, high-speed cameras inspect the chocolates for surface defects, rejecting any that are misformed or marred. If filled or layered chocolates are being produced, the process diverges earlier. In that variation, the molds receive only a thin chocolate shell in the first deposit. These shells are then cooled, filled with praline, ganache, or fruit paste through precision piston fillers, and then sealed with a final layer of tempered chocolate before full cooling. Back on the main line, the finished solid chocolates enter the enrobing tunnel if they require coatings. This consists of a continuously flowing curtain of tempered chocolate falling from a weir system. The chocolates pass beneath the curtain on a wire mesh belt, receiving a uniform coating. Excess chocolate is blown off the bottom by air knives positioned beneath the belt. After enrobing, the products move through another cooling tunnel. This secondary tunnel is slightly longer and maintains cooler airflow at 6-8 degrees Celsius to ensure the coating sets with a uniform sheen. Inside, multiple temperature zones gradually reduce the product temperature to avoid bloom or condensation. Next is the decorating phase. This station uses robotic arms fitted with ultra-fine nozzles and stampers. The arms are guided by a 3D vision system to identify the orientation of each piece. Depending on the product, they may apply fine chocolate stripes, edible gold dust, cocoa powder, or even embossed logos using heat press stamping heads. Some lines include a nut topping mechanism that drops single pistachios or almonds onto the still soft chocolate surface with pneumatic precision. From here, the chocolates move to the buffering conveyor. This is a serpentine belt that temporarily holds products in case downstream machines slow down or halt. It prevents product collisions and maintains production flow without pause. Once flow resumes, the chocolates proceed to the wrapping line. The wrapping process begins with a high-speed feeder system. Chocolates arrive in single file along a narrow conveyor aligned by adjustable guide rails. As they approach the wrapping unit, an optical sensor scans each piece to verify orientation and spacing. A star wheel indexing system captures each chocolate in a rotating pocket, ensuring it enters the wrapping machine at precisely timed intervals. For individually wrapped pieces, the wrapping style depends on the product type, either fold wrap, twist wrap, or flow wrap. Fold wrap is used for rectangular or square chocolates. A continuous roll of foil, ends, often metallized polypropylene or laminated aluminum, feeds into a cutting station. A servo-driven knife slices the foil into perfectly sized sheets. A vacuum picker transfers each sheet onto a wrapping plate where a chocolate rests. Pneumatic folders quickly tuck each edge of the foil around the chocolate with clean, creased folds. And heated plates press the final seam to ensure adhesion without adhesives. In twist wrapping, used for rounded or pillow-shaped pieces, the chocolates are dropped into film pockets on a rotating turret. As they spin, two heated jaws grip the ends of the film and twist them in opposite directions in a single, fluid motion. The result is a tight double twist at both ends with no glue, secured purely by friction and film memory. Flow wrapping is reserved for bars or longer chocolates. Chocolates move onto a horizontal flow wrapper in perfect rows. A forming box folds a continuous film web into a U-shape around the moving product stream. Longitudinal sealing wheels fuse the film along the bottom seam using heat and pressure. Rotary end sealers then crimp and cut between each chocolate in one continuous motion. The result? A tight, seamless pillow pack with serrated edges. Once wrapped, products pass under a metal detector integrated with an automatic reject arm. Any contamination triggers an immediate air jet that diverts the product off the main line without interrupting flow. Approved chocolates continue to the labeling and grouping section. For chocolates requiring labels or tamper-evident seals, a label applicator aligns pressure-sensitive labels onto the wrapper surface with micron-level accuracy. For sealed tags or holograms, a rotary arm applies the label with static discharge to eliminate air pockets. High-speed vision systems verify placement and orientation, rejecting any misaligned units. Next, the wrapped chocolates are grouped into sets for final boxing. This is handled by a Delta robot pick-and-place system. Using 3 arms mounted on a gantry and guided by overhead cameras, the robots lift chocolates from the conveyor and deposit them into plastic or cardboard trays. The trays are held on index pallets that move step by step beneath the robot's reach. Depending on the SKU, arrangements may be linear rows, nested pyramids, or offset diagonals. If the product is a boxed chocolate assortment, the process diverges again. Assorted trays begin with an injection molded plastic insert, which is automatically placed into a folding carton. Chocolates are sorted by type and delivered to multi-head pickers. Each picker arm uses vacuum suction or soft rubber grippers to lift specific chocolates and place them in precise tray compartments. The sequence is synchronized to ensure correct assortment patterns. No duplicates, no gaps. Once loaded, these trays move to the lid application station. A folding carton blank is fed into a forming mandrel, where pneumatic fingers erect and glue the box around the insert. A transparent film or foil seal is sometimes heat applied across the top, shrinking snugly into place. Then, a decorative lid is pressed on with a spring-loaded arm to achieve a flush seal. If a rigid luxury box is used, an entirely separate line assembles it. Die-cut cardboard is laminated with printed paper and hot-pressed into box forms. Magnets or ribbon closures are inserted automatically by articulated tools. The finished boxes are then transferred via robotic arm to receive their filled trays. From here, final boxing and case packing begins. Chocolates, now individually wrapped or boxed, arrive on a wide accumulation belt. Automatic collators organize them into bundles of 6, 12, or more, depending on shipping unit configuration. These bundles are pushed into carton erectors where flat corrugated blanks are folded around them, glued and pressed shut. Some lines use wraparound case packers. In this method, the grouped products are held stationary as a blank corrugated sheet is wrapped around all sides. Mechanical arms fold the flaps, apply hot melt glue, and compress the bundle into a sealed shipping case. These cases exit onto a short conveyor where industrial inkjet printers mark each side with batch numbers, timestamps, and QR trace codes. The case is then moved to the palletizing zone. Here, a robotic arm with a vacuum plate or gripper head arranges cases onto pallets. Each layer follows a programmed stacking pattern, alternating orientations for stability. After each layer, a slip sheet may be inserted by an automated feeder. Once the full stack is complete, often up to 2 meters high, the pallet is conveyed to a stretch wrapping machine. The stretch wrapper features a rotating turntable and a film carriage that moves vertically. As the table spins, the carriage stretches and applies multiple layers of plastic film under tension. This secures the load tightly and protects against moisture and dust. Some systems include a top sheet applicator that lays a waterproof plastic sheet across the top before wrapping. Finally, the fully wrapped pallets are conveyed through a weight check station and scanned by a vision system for final verification. They are now ready for shipment. A precisely manufactured, delicately handled series of chocolates transformed through over 24 distinct mechanical stages from raw bean to boxed luxury. For filled and layered chocolates, the factory employs a specialized multi-stage molding line. This system operates on a closed-loop conveyor that continuously cycles polycarbonate molds through a sequence of precisely timed stations. Each mold contains multiple cavities, and every station in the circuit performs a distinct action in the assembly of complex, filled products. The process begins with the shell forming station. A depositor head releases a measured volume of tempered chocolate into each mold cavity. Immediately, the molds move to a tilting station, where they are flipped and vibrated simultaneously. Centrifugal force causes the chocolate to coat the sides and bottom of each cavity evenly, leaving a hollow center. Any excess chocolate flows out and is reclaimed. After inversion, the molds pass under a chilled airflow, rapidly setting the shell. Once the shell is solidified, the molds continue to the filling station. This unit features servo-controlled piston depositors mounted above each cavity. The fillings are stored in heated hoppers to maintain fluid consistency. These can include hazelnut praline, fruit compotes, flavored ganache, caramel, or nut pastes, each delivered through dedicated nozzles. The depositors lower and inject precise quantities into each chocolate shell without disturbing the walls. Viscosity is controlled via inline heating coils wrapped around the filler lines. Every filling passes through mass flow meters to ensure consistency across thousands of units. Between each product type, CIP, clean-in-place systems, purge the lines with high-pressure heated water, followed by compressed air to eliminate cross-contamination. Next, the filled molds pass through a brief cooling tunnel. This lowers the filling temperature just enough to create a thin surface skin, ensuring it doesn't mix with the final chocolate seal. At the cap sealing station, another depositor head applies a top layer of tempered chocolate, sealing each cavity shut. This chocolate is deposited with high precision, covering the filling completely and fusing to the shell edges. Vibration tables beneath the molds remove trapped air and ensure a flush finish. The molds then enter a long cooling tunnel, typically spanning over 10 meters. This tunnel contains multiple chilled zones that gradually reduce product temperature from 30 degrees Celsius to under 10 degrees Celsius. The slow, staged cooling prevents shrinkage or cracking and allows the chocolate to fully contract away from the mold walls. Once cooled, the chocolates are ejected mechanically. Pneumatic plungers behind each mold cavity gently push the finished pieces downward onto a soft conveyor. These filled chocolates proceed to surface treatment. For layered chocolates, a similar system is used with key variations. After the first shell is deposited and cooled, a layer of inclusions, such as crushed nuts, cookie pieces, or fruit granules, is sprinkled into the mold by an oscillating vibratory feeder. A light pressure roller presses the inclusions into place. Then, a layer of filling is added, followed by a capping layer of chocolate. This creates a tri-layered cross-section when cut or bitten. Aerated chocolates follow a different method entirely. Here, the chocolate is first fed into a pressurized vacuum chamber. Under controlled vacuum, nitrogen gas is injected into the chocolate stream through a sparger, a perforated titanium rod. The gas forms microbubbles, which are then locked in by suddenly returning the chamber to atmospheric pressure. The now aerated chocolate has a mousse-like texture, yet remains stable once cooled. This aerated mixture is deposited into molds using modified volumetric heads that prevent bubble collapse. Because of the internal gas structure, aerated chocolates are cooled more gently to avoid rapid contraction. They pass through a specialized tunnel with fine-tuned temperature gradients that stabilize the internal structure. Some advanced variations include dual flavor split molds. These use two separate depositors operating in tandem, each filling half of the mold cavity with a different chocolate, such as milk and white or dark and ruby. A precision divider plate inside the nozzle ensures a clean, vertical split. The chocolates are deposited simultaneously, then vibrated and cooled, just like single origin types. Another variant involves inclusions in the chocolate itself. Before deposition, the base chocolate is mixed with particulate ingredients in a jacketed mixing bowl. These include puffed rice, freeze-dried fruit bits, chopped nuts, or biscuit crumbs. Agitators inside the bowl maintain even suspension. A positive displacement pump pushes the mixture through a large bore pipe to prevent clogging. Depositor heads with wider nozzles are used to handle the textured mass. For decorative layering, some lines use transfer film technology. A thin acetate film, printed with edible cocoa butter designs, is cut into sheets and placed on the bottom of each mold before chocolate is deposited. When the chocolate sets, the design transfers from the film onto the chocolate surface, creating intricate visual patterns. After cooling, the film is peeled away, leaving behind a vivid imprint. In other cases, chocolate pieces are stamped with embossed patterns or logos. After demolding, the chocolates move under a stamping head fitted with a heated metal die. The die is pressed lightly onto each piece, embossing it with a brand mark, pattern, or crest. The metal stamp is kept at 32 degrees Celsius, just warm enough to soften the surface without damaging structure. At this point, finished chocolates, whether filled, layered, aerated, or decorated, are directed toward the enrobing and topping station, if required. Some filled pieces receive an extra chocolate shell by passing through the enrobing curtain. Toppings such as sea salt flakes, crushed pistachios, or cocoa nibs are dispensed through multi-channel feeders synchronized with the belt speed. Each topping module includes a vibration sieve that controls granule size and drop rate. Sensors monitor belt occupancy to ensure no topping lands between products, minimizing waste. A gentle pressing roller may follow to embed toppings into the soft coating before cooling. Some premium chocolates are dusted with edible luster dusts or shimmer coatings. These powders are dispensed in an ultra-fine mist using electrostatic sprayers. The particles are positively charged as they exit the nozzle, adhering uniformly to the negatively charged chocolate surfaces. This creates a metallic or pearlescent finish with minimal overspray. For chocolates that require a hard shell glaze, a final step involves a rotating drum polisher. Chocolates are fed into the drum, which tumbles them gently while applying a thin mist of food-grade shellac or gum arabic. Internal warm air jets dry the glaze instantly, leaving a glossy, protective surface. Before reaching packaging, all finished chocolates pass through a multi-stage inspection tunnel. This includes laser-based shape detection, surface color analysis, and infrared temperature scanning. Products outside tolerance limits are ejected into designated bins. The final stage begins at the primary packaging line, where individual chocolates are grouped, positioned, and inserted into final, retail-ready formats. This step varies depending on the packaging style: rigid boxes, folding cartons, sleeve wraps, trays, tins, or multi-compartment assortments. Each format requires a dedicated configuration of pick-and-place systems, folder gluers, and sealing units. For rigid box assortments, chocolates arrive on an indexed belt and are picked by high-speed Delta robots equipped with vacuum suction heads. These robots place the chocolates into thermoformed plastic inserts, which are held stationary within open-bottomed rigid boxes. The inserts have precisely molded cavities matched to the contour of each chocolate piece. The robot arms adjust their speed and angle using dynamic feedback from overhead 3D scanners to avoid any misalignment. Once all cavities are filled, the boxes proceed to a film sealing station. Here, a roll of transparent BOP film is unwound, cut into sheets, and laid across the surface of the tray. A heated sealing plate presses the film into place, fusing it along the box edges to create a tamper-evident, airtight seal. The temperature of the sealing head is closely monitored by embedded thermocouples to maintain optimal adhesion without distorting the tray. For folding cartons, a different approach is used. Flat carton blanks, pre-printed and die-cut, are fed from a magazine stack into a carton erector. Mechanical arms fold the blank along pre-scored lines and apply hot melt glue in strategic points using precision nozzles. The forming mandrel compresses the carton into shape as it moves along the conveyor. Simultaneously, chocolates are grouped upstream by a collator belt, which aligns them into patterns matching the carton's internal layout. A pneumatic pusher slides each group into the open cartons as they move past. Once filled, the top flaps are folded and glued shut in a continuous motion. Some cartons are sealed with ultrasonic bonding, especially when glue-free closures are preferred. Specialty packaging formats, like sleeve-wrap trays, begin with a plastic or cardboard tray filled with chocolates using robotic placers. A printed sleeve, flat and folded, is then placed over the tray. A servo-controlled banding unit wraps the sleeve snugly and applies a heat pulse to seal the overlap. These sleeves often include die-cut windows or embossing, requiring precise alignment during application. For metal tins or embossed boxes, an overhead conveyor delivers empty tins into position beneath the filling heads. Chocolates are stacked by robotic arms, using multi-head grippers that rotate to fit varied geometries. Once filled, the tins are lidded by a lid placement mechanism equipped with pneumatic actuators. The lid is pressed into place with a calibrated force to ensure a snug fit without warping the metal structure. In premium lines, inserts and accessories are added next. These include product guides, tasting menus, or promotional leaflets. A sheet feeder places the inserts into each box before final closure. In some configurations, a robotic arm adds a protective paper layer or a foil cover between the chocolates and the lid. When ribbon closures are required, a secondary robot wraps and ties the ribbons automatically using twin spindle tensioners and soft grippers. After primary packaging, products move into the overwrapping unit, especially for premium and seasonal items. A continuous film roll feeds through a forming collar to enclose each box. A fin sealer applies pressure and heat along the bottom seam, while side sealers tuck and seal the ends into neat folds. A cooling plate downstream sets the film structure immediately after sealing. Optional tear strips or easy open tabs are applied at this stage. These are pre-cut film sections with embedded threads or adhesives that allow consumers to open the product without tools. A precision applicator adds them just before the film is sealed, embedding them into the plastic without disturbing box integrity. Next is batch labeling and coding. An inkjet printer or laser etcher marks each box with its batch number, manufacturing date, expiration date, and unique identifier. For export products, a vision verification system checks every printed code in real time and compares it against the product database. Any mismatch causes an automatic ejection by a pneumatic diverter. Then, boxes enter the case packing line. A robotic case packer arranges the boxed units into shipping cartons according to a pre-programmed pattern. Each case is assembled from flat blanks in an automatic erector. Once filled, the case is sealed using a high-speed tape applicator or hot melt glue system. The type of seal depends on the distribution channel and climate conditions expected during transit. Some boxes are stacked vertically, while others lie flat, depending on product fragility and presentation. If protective dunnage or air cushions are required, an integrated dispenser adds these into the case before sealing. Completed cases are printed with destination codes and passed through a check weigher, which confirms that each box is within expected weight tolerances. At the end of the line, full cases are transferred to the palletizing system. A robotic palletizer uses a vacuum plate or mechanical gripper to stack the cases onto pallets in a staggered pattern. The stacking sequence is designed for maximum load stability. Between layers, corrugated slip sheets are automatically inserted from a magazine. Once the pallet reaches the target height, typically 1.8 to 2 meters, it is conveyed to a stretch wrapping machine. The turntable rotates the pallet while a film carriage moves vertically, wrapping it in multiple layers of stretch film. Tension sensors ensure that the film applies consistent pressure without crushing the product. For export pallets, a top sheet dispenser adds a final moisture barrier before wrapping is completed. The final wrapped pallet moves to the finished goods staging area. Here, each pallet passes through a scanning tunnel that records its dimensions, weight, and barcode data into the warehouse management system. Automated guided vehicles, AGVs, retrieve the pallets and deliver them to temperature-controlled storage areas where ambient humidity and temperature are monitored continuously. In some specialized lines, climate conditioning is introduced post-packaging. Products enter a controlled chamber that simulates various storage conditions. For instance, rapid temperature cycling from 10 degrees Celsius to 30 degrees Celsius to ensure product stability. Chocolates are held in this chamber for several hours before release to shipping to verify that they maintain integrity under stress. Before release, a final quality sampling system selects random units from each production batch. These samples are conveyed to a physical and sensory testing station, where robotic arms manipulate the products through breakage resistance tests, surface gloss readings via reflectometers, and cross-sectional scanning via laser slicers. The internal structure is analyzed for air pockets, alignment of layers, and crystallization consistency. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. Agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill confirmation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella Be Ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor, leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.0-1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella Be Ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Celsius within 2 minutes. Simultaneously, Nutella filling is prepared in a separate processing room using a continuous mixing system. Ingredients including refined sugar, vegetable oil, skimmed milk powder, cocoa, and hazelnut paste are dosed using mass flow meters and pneumatic transfer lines. Mixing occurs in a double-jacketed emulsification vessel with counter-rotating impellers operating at 800 to 1200 RPM. The temperature is held between 40 degrees and 45 degrees C during mixing to maintain fluidity and preserve emulsion stability. The finished Nutella filling is pumped through heat-insulated stainless steel piping into buffer tanks connected to multi-head depositor units. These depositors are aligned with the conveyor lanes carrying the pre-formed wafer shells. Each depositor nozzle dispenses a precise amount of filling, usually between 12 and 16 grams, into the hollow cavity of each wafer. Fill weight is monitored using inline load sensors that reject any units outside the tolerance band of plus 0.3 grams. To prevent air entrapment during deposition, the filling nozzle retracts during injection at a synchronized rate, matching the filling viscosity and back pressure. Cream flow is assisted by low-pressure nitrogen to maintain a consistent stream and eliminate pulsing. After filling, each shell passes through a cooling tunnel maintained at 10 to 12 degrees to solidify the fat phase of the filling and prevent oil migration into the wafer wall. Following cooling, a pre-molded wafer lid is applied to seal each filled shell. These lids are formed from the same dough and are baked separately on a synchronized rotary system. A robotic arm equipped with vacuum suction cups picks and places each lid onto the open cavity. An edible adhesive compound, typically a glucose-based syrup, is applied to the perimeter edge to create a bond. Pressure rollers compress the lid and base together for mechanical adhesion. After sealing, each unit passes through a mechanical inspection station. High-speed cameras and laser profilometers verify shell integrity, alignment, lid placement, and overall dimensions. Any product with cracks, offset seals, or excessive height deviation is automatically rejected via pneumatic diverter arms. Approved units move into the packaging preparation line. Packaging begins with flow wrapping. Individual Nutella Be-Ready units are spaced on timing belts and fed into the wrapping machine using servo motor-controlled pushers. Wrapping film is fed from a roll and formed around each unit via a forming collar. Horizontal and vertical seals are applied using heated sealing jaws that operate at 130 degrees, 145 degrees Celsius. Modified atmosphere packaging is implemented via nitrogen gas injection prior to sealing to displace oxygen and extend shelf life. Each flow-wrapped unit is scanned by barcode readers and printed with date codes and traceability numbers using thermal inkjet printers. Units are counted and grouped into sets of 6 or more, depending on market configuration. Grouping is performed using star wheel collators, which align the units into rows for secondary packaging. Secondary packaging uses flat fold cartons erected via vacuum cup pick-and-place systems. Hot melt glue is applied via nozzles to predefined folding flaps, which are pressed closed by mechanical arms. Each carton receives printed labels containing product name, nutritional data, batch code, allergen information, and certification marks. Cartons are weighed for content verification and stacked into larger corrugated shipping boxes using layer-forming robotic packers. Palletizing is performed by 6-axis robotic arms with end effectors designed to grip multiple boxes per cycle. Standard Euro or industrial pallets are loaded based on customer logistics requirements. Pallet patterns are configured to ensure structural stability and airflow clearance. Once loaded, pallets are wrapped using stretch film machines that apply 250% pre-stretched film to secure load integrity during transit. Each pallet is tagged with a pallet license plate containing full production metadata, including line number, production date, shift code, storage conditions, and destination route. Pallets are moved into finished goods, storage warehouses with temperature and humidity control systems set to maintain between 18 degrees Celsius and 20 degrees Celsius, with relative humidity under 60%. Pallet positions are recorded using warehouse management systems with RFID scanners and barcode tracking. Throughout the production process, all inputs, outputs, and in-process conditions are monitored by a centralized SCADA system. Parameters such as oven temperature, mixer torque, depositor cycle counts, wrapping seal integrity, and product rejection rates are logged and archived. Alerts are generated automatically for any deviation outside programmed thresholds. Operators access these systems via HMI touchscreens placed at each station. Sanitation protocols are applied on a rotating schedule. Dough preparation lines are cleaned with dry brushing, followed by ethanol-based surface wipes. Cream handling equipment undergoes full CIP cycles involving alkaline wash, acid rinse, and sterile water flush, validated with conductivity and pH sensors. Wrapping and cartoning stations are cleaned with compressed air, brush downs, and isopropyl surface sanitizers. Swab samples are taken post-cleaning and tested for microbial load. Preventive maintenance is performed weekly on all forming dies, depositor heads, conveyor bearings, and sealing modules. Wear components are replaced based on run-hour tracking. Calibration is conducted daily on dosing equipment, weighing scales, and thermocouples. All calibration records are maintained in compliance with regulatory documentation standards. Product testing occurs hourly. Samples are collected from each production lane and evaluated for weight, length, height, filling content, shell texture, seal strength, and packaging tightness. Sensory analysis includes bite resistance, shell-to-filling ratio, and flavor consistency. Non-conforming samples trigger root cause investigations documented in deviation reports. The entire Nutella Be Ready manufacturing process is standardized to allow for duplication across multiple production facilities with identical output quality. Parameters are optimized to prevent moisture migration, mechanical breakage, and oil separation, which are common defects in filled wafer-based snack formats. Final product shelf life is tested under accelerated and ambient conditions to verify packaging efficacy. Chips Ahoy. Cookie manufacturing begins with bulk ingredient handling systems that store raw materials in separate silos or intermediate bins under controlled conditions. Low moisture, fine milled wheat flour is pneumatically conveyed from outdoor silos into batch weigh hoppers located above the main mixing area. Granulated sugar, brown sugar, cocoa solids, salt, and baking soda are stored in indoor silos or gravity-fed bins and fed into weigh stations using screw feeders with plus 0.1% dosing precision. Vegetable shortening and liquid invert sugar are stored in stainless steel jacketed tanks with continuous recirculation to prevent phase separation. The shortening is heated to maintain fluidity at 45 to 50 degrees Celsius, and the invert sugar is pumped at a constant rate through positive displacement pumps. All liquid and dry ingredients are tracked using an integrated batching control system that verifies real-time mass flow and batch integrity using load cells and flow meters. Each batch is loaded into a planetary batch mixer with a dual paddle agitator system. Mixing follows a 3-stage, time-controlled sequence. First, creaming of shortening and sugars is performed for 3 to 4 minutes at low speed. Next, flour and leavening agents are incorporated at medium speed for an additional 3 minutes. Finally, the mixture is scraped down and mixed on high speed for 1 to 2 minutes until a homogeneous dough with uniform texture and target moisture content of 18 to 20% is achieved. Temperature sensors monitor the dough throughout mixing to ensure it remains within the 20 to 24 degrees Celsius range. Overheating is prevented by jacketed cooling systems circulating chilled glycol solution. Once the dough is fully mixed, it is discharged into a stainless steel hopper that feeds a cookie depositor via auger conveyors. Before entering the depositor, chocolate chips are metered into the dough using volumetric feeders to achieve a distribution ratio of approximately 20% by weight. The cookie depositor uses servo-controlled pistons to extrude uniform dough portions directly onto a continuously moving Teflon-coated oven band. Deposit weight per cookie is calibrated to between 18 and 21 grams, depending on SKU. Deposited dough pieces are spaced using optical sensors to maintain consistent center-to-center distance and allow for uniform spread during baking. Each dough piece is flattened slightly by a roller to control shape retention. The baking oven is a hybrid convection and radiant tunnel oven with multiple independently controlled heating zones. Total bake time is typically between 8 and 11 minutes. The oven band runs at a set speed that is continuously adjusted by a PID controller based on real-time surface temperature and humidity readings. Oven zone temperatures range from 160 degrees Celsius in early zones to up to 210 degrees Celsius in final zones to ensure progressive starch gelatinization, moisture evaporation, Maillard reaction, and fat migration. Cookies are monitored during baking using infrared pyrometers that measure surface temperature. Steam injection systems in early oven zones are optionally used to control surface moisture and prevent excessive cracking. Exhaust fans in later zones remove excess humidity and volatile compounds. By the time cookies exit the oven, internal moisture content is reduced to between 3 and 5%, ensuring shelf-stable texture and microbial safety. Upon exiting the oven, cookies are transferred onto a wire mesh cooling conveyor system. Ambient air is directed from below and above the belt using axial fans to achieve uniform cooling to under 30 degrees Celsius in less than 3 minutes. Sensors at the end of the cooling belt check surface temperature before transferring cookies to the inspection area. Conveyor vibrations are minimized to prevent cookie breakage during transfer. Each cookie passes under a vision inspection system equipped with high-resolution cameras and infrared lighting. Software algorithms evaluate cookie shape, surface cracking, chip dispersion, color uniformity, and diameter tolerance. Any cookies failing to meet visual standards are rejected using high-speed air jets. All rejected cookies are weighed, logged, and diverted to waste bins for offline handling. Approved cookies move to the packaging station via a system of vibratory conveyors that align and group the cookies into required configurations. For multi-pack packaging, cookies are grouped into stacks using rotary collators and staged for wrapping. Individual flow packs are created using horizontal form-fill-seal machines. Film is pulled from rolls, shaped around each cookie group, and sealed using heated crimp jaws operating at 130 to 150 degrees Celsius. Modified atmosphere packaging may be used with nitrogen flushing to reduce oxygen and delay lipid oxidation. Each wrapped package receives a printed date code, batch code, and line identification number using thermal inkjet printers synchronized with the conveyor belt. Packages are weighed on inline check weighers with rejection arms for any unit falling outside of mass tolerances. Wrapped units are inserted into cartons using robotic pick-and-place arms with vacuum grippers. Cartons are sealed with hot melt glue at 165 degrees C and pressed under controlled pressure to ensure full adhesion. Secondary packaging lines aggregate cartons into shipping cases. Cases are erected from flat blanks, filled automatically, and closed with either glue or tape depending on distribution requirements. Completed cases are printed with pallet codes, production timestamps, and destination routing labels. Automated guided vehicles, AGVs, or roller conveyors transfer cases to palletizers. Palletizing robots layer the cases using defined stacking patterns optimized for pallet stability and load efficiency. Each pallet is scanned for completeness using weight and barcode validation before being stretch wrapped in polyethylene film at 250% pre-stretch. Wrapped pallets are moved to finished goods warehouses with controlled temperature and humidity, typically 18 to 20 C and 50 to 60% RH. Every stage of the process is controlled and logged using a manufacturing execution system, MES. Batch records include ingredient lot numbers, mixing parameters, bake curves, oven temperatures, deposition weights, packaging counts, inspection rejections, and finished product quantities. Quality control technicians collect hourly samples to perform destructive and non-destructive testing on cookies. Tests include diameter measurement with calipers, moisture analysis via moisture, analyzer, texture profile analysis using 3-point bending rigs, and chip count per cookie via manual visual audit. Organoleptic tests include bite resistance, sweetness intensity, and flavor profiling under controlled conditions. Data is stored electronically and checked against specification ranges defined in the product specification documents. Production lines are cleaned on a rotating schedule. Between batches, dry cleaning is performed using brushes and vacuum systems to remove flour dust and crumbs. At daily intervals, equipment is disassembled and sanitized using foaming alkaline cleaners, followed by water rinses and food-safe sanitizers. Chocolate lines undergo specialized cleaning to prevent fat bloom and cross-contamination. Allergen control zones are enforced through physical separation of lines, color-coded tools, and allergen-specific cleaning validations. Swab tests for protein residues are performed on high-contact surfaces after each cleaning cycle. If any allergen residue exceeds the defined limit, cleaning is repeated and verified before production resumes. Downtime events such as depositor jams, film feed interruptions, or oven temperature deviations are tracked via the line control system. Operators record the event time, cause, and corrective actions. Line productivity is measured using overall equipment effectiveness (OEE) metrics, including availability, performance, and quality yield. Preventive maintenance on mixers, ovens, conveyors, depositors, and packaging machines is scheduled based on runtime hours. Critical components such as servo motors, bearings, seal jaws, and roller chains are monitored for vibration and thermal performance. Spare parts inventory is maintained in real time using a computerized maintenance management system, CMMS. Finished product samples are retained from each batch for shelf life testing. These samples are stored under accelerated and ambient conditions and tested at intervals for texture degradation, moisture migration, lipid oxidation, and packaging integrity. Results are used to confirm product expiration dates and to evaluate packaging material performance. All operations conform to global food safety standards such as GFSI benchmarking and are subject to internal audits and third-party certification. Traceability systems allow for immediate upstream and downstream tracking of all product components within minutes of any query. Any deviations from process controls trigger root cause analysis under a corrective and preventive action (CAPA) protocol.